Chapter 22 will focus on water pollution in AP Environmental Science, so let's dive. First thing is the Gulf of Mexico's annual dead zone, also known as a hypoxia zone, because it screws up the oxygen. The Mississippi River Basin, think about it, goes almost all the way over to Idaho, all the way through Pennsylvania, and parallels the Mississippi Basin. And what happens is we get huge inputs of nutrients like phosphates and nitrates that rush all the way down into the Gulf. As a result, it goes through eutrophication, and we get a depletion of dissolved oxygen in the Gulf of Mexico's bottom layer of water. So anything that naturally would live on that bottom layer would actually not be able to survive. So fishing, particularly for things like oysters, is terrible. It also disrupts the nitrogen cycle. All those sources and flushing of all those states into the basin, all that nitrogen goes with it. What that does is it depletes all the natural vegetation that would occur along the Mississippi River, from it. So you can see the Mississippi Basin right here, and all those nutrients from those regions, from all those tributaries, flow into there. And of course, in the hypoxia zone, another little aerial picture of it right here. And of course, the dead zone would be at the delta, or at the below the delta, this region right in here. So fishing is very bad down there. Now, how do we test for pollutants? Many different ways. We can do fecal coliform counts. Fecal coliform is basically like cow, or could be even human poop. The E. coli bacteria that exists in there is what we test for. Of course, that can be toxic to us. It's really weird, but we have that E. coli living in our intestines, but if it should end up in our blood systems, we can become toxic. We can do bacterial source tracking. So now with this idea of BST is we can actually figure out where that bacteria came from due to DNA analysis. Biological oxygen demand, or BOD, is the amount of oxygen that bacteria are using to decompose. So in other words, aerobic bacteria. If we have a very high biological oxygen demand, in other words, they are demanding lots of oxygen, we've got lots of bacteria, which means we've probably got lots of pollutants, because bacteria likes to get rid of those pollutants, which is a good thing. We test for inorganic things like phosphates, ammonia, nitrates, organic substances, even taking a look at the plants that would exist in there. Turbidity of the waters, how clear it is. Indicator species, you can see some on the right. Some of those are more sensitive than others. And we can even look at heavy metals within a stream that are being put in from like neighboring industry or factories or things of that nature. Water pollution can cause illness, death, humans, other species, disrupts ecosystems. The main sources are agriculture. Number one, agriculture is the number one polluter. Of course, we need to eat, so farmers need to grow food, need to make some money, need to feed us, and unfortunately put a lot of inorganic fertilizers on, which gets into our watersheds. Industrial facilities, number two, mining is terrible too. Growth of the human population, rate of resource use really makes it increasingly worse. Are getting dirty. Luckily in the United States we have very good laws for this. So water pollution is deemed a change in water quality that can harm organisms or make water unfit for human use. So keep in mind, a lot of people may have water, they may even have fresh water, but it may not be clean, and in that case what happens is they can't survive. There's two ways of looking at the sources. There's point source and non-point source. Point source is literally you can point at where the toxin is coming from, or the pollution. Very easy to identify and monitor. So take a look at this lovely picture of that terrible red stuff. You can literally point, you know exactly where you can trace back where that pipe is going and contaminants are coming from. Non-point sources are much harder. Broad, diffuse areas, really difficult to identify and control, very expensive to clean. You can see a picture right here. There's this river system here, or this pond system, and we've got that sludge in there. It may be coming from the farmer on this side, may be coming from the farmer on that side, may be coming from way down the road. This may come from neighborhoods. Maybe you live in a huge neighborhood and one person is dumping some gasoline where they're not supposed to be dumping gasoline, or oil. We don't know exactly where it's coming from. That's really for biologists. So again, leading causes of water pollution, agriculture. Number one, the sediment is eroded from the public lands when it rains or floods. Fertilizer and pesticides are included. Industrial facilities, we get lots of heavy metals, we get lots of organic chemicals that are used. Things like gasoline. Gasoline is an organic chemical. Organic is also things like oil. Erosion, toxic chemicals. Mining is very dirty. In the mining unit, we may have talked about cyanide heap leaching, which is when they use impurities or the gangue of ore And when it's attached to the gold, those impurities are oftentimes taken off with cyanide. Cyanide is a toxin that then gets into the environment. We can get infectious diseases. We'll take a look at these in a little bit. Contaminated drinking water. Milwaukee is a prime example of that, because in the early 90s we got this magical little protist called the Cryptosporidium that made it through our system and got lots of people sick, actually killed some people too, with compromised immune systems. Sadly, an estimated 1.6 million people every year die from contaminated water, mostly under the age of 5, which here is a chart that's very important. Infectious agents like pathogens that cause disease are things like bacteria, virus, protozoa, and parasites. Giardia would be an example of this. Obviously, the parasites, protozoa particularly, would be things like Cryptosporidium. We could have cholera in here, which is a bacteria. Major sources are human and animal waste. Yeah, you heard it, human waste. If somebody has a leaky septic system, boom, in the drinking water supply. Oxygen-demanding waste, in other words, those are wastes where aerobic bacteria need to dissolve it, are things like animal waste, plant debris. This may be from sewage. It's well known in the Mediterranean region. Lots of those nations put the raw sewage right into the Mediterranean Sea, and then we get lots of bacteria that needs to eat that. That's aerobic, and then what happens is we don't have much oxygen, so plants and animals die. Animal feedlots, food processing facilities, paper mills. Plant nutrients, we've talked extensively about that, nitrates and phosphates. Where does that come from? Again, sewage, animal waste, inorganic fertilizers, organic, oil, gasoline, plastics, pesticides, cleaning. We'll see some pictures later of just how nasty it is in the oceans and how polluted they become from things like plastics. Inorganic chemicals, acids, bases, salts, metal compounds. Sediments, things like soil and silt. Yes, even if we have excessive soil that is rushed off into a water system, that can occlude it so much where fish can't survive or plants can't grow because it's too dark. Heavy metals are things like lead and mercury and arsenic, a lot of times from industry, from landfills. Thermal is heat. Heat is generally from electric power plants, from nuclear plants, from industrial plants, where they cool off their machines with water from a lake or a river, and then what happens is they return it, and that causes pollution. So, streams and rivers around the world are extensively polluted, but streams and rivers are moving. They generally can cleanse themselves of many pollutants if we don't overload them, because they are moving. The vegetation, whether it be in the water, on the side of the water, generally does a good job of taking the pollutants. Not that it's okay to pollute these areas. Adding extensive nutrients to lakes from human activities can disrupt their ecosystems, and prevention of such pollution is more effective and less costly than cleaning it up. So keep that in mind. Let's prevent it before we put it into our ecosystems, because once a river takes it, or once it gets, not easy. We could try to dilute these pollutants. That was kind of the answer about 20 years ago, and we don't really rely on that much anymore. We could use biodegradation of waste by bacteria, but that takes time. I'm going to show you a picture in the next slide of something called the oxygen oxygen sag curve, which is very important to know, so make sure you learn it. Breakdown of biodegradable waste by bacteria depletes oxygen. This guy works is this. First of all, take a look at what's given. Dissolved oxygen parts per million, very high, very high, very high. Biological oxygen demand, remember what that is the amount of bacteria that requires oxygen. So, what happens is we have a point source pollutant in this river system, keeping in mind the river goes that way. What happens is we get this pollutant in here, and what's going to happen is bacteria really likes to break this stuff down, which is super cool. But what happens is the amount of bacteria goes up. They need oxygen. As that goes up, the amount of oxygen goes down. As that happens, the creatures that can live in here, look, we have nice bass and perch and basically that in here, which are game fish, they need high levels of oxygen. Happens to be 8 parts per million in this case. And what happens then, we get things like leeches and carp and nasty stuff, gars that live in this region right here. And then what happens is slowly the bacteria destroys it as it's going down. And what happens to the amount of BOD as it goes down? As that goes down, the dissolved oxygen content is going to go back up, and we get nice little fish like this. So, with that said, we have a clean zone. We have a decomposition zone. So what's happening is we're decomposing that bad bacteria. we get a septic zone. Septic means pretty much toxic, not much is going to live there. We've got lots of little leeches and things like that. We will have bacteria in there, but it's anaerobic. We don't have much oxygen, so we have anaerobic bacteria in there. We get a recovery zone, and boom, we're clean again. Now, a couple interesting case studies, 1970s. Water pollution control laws finally came out, and that kind of paralleled the EPA's advancement. And an interesting story is the Cuyahoga River of Ohio. It was so polluted, particularly with oil products, that it literally started on fire. This was an eye-opening experience. I believe that was 1972. What happened is that kind of helped us get the Clean Water Act because we knew it was so polluted, and they were getting drinking water from it at one time too. Thames River in Great Britain, of course, that went through the great industrial era. What happened is it got polluted, particularly with coal sediments, and of course what happened was it became very polluted. Those are both success stories. We've cleaned those up drastically with new laws. Contamination, of course, of toxic inorganic and organic chemicals by industry and mines are half of the world's 500 major river systems are polluted with things like untreated sewage. We in the United States have very good treatment facilities, which we'll talk about down the road. A lot of nations don't. A lot of industrial waste is dumped directly into here too. Water often is used for human activities, so what happens is a person or a company will be dumping in toxic solutions upstream, and you're bathing downstream from it or getting your drinking water. Not good. Look at this terrible situation. This is in Southeast Asia. You can see basically all that debris in there, and look at how nice and brown and chocolatey flavored that water is. Actually, it looks very polluted. Now, lakes. Lakes are a little bit less effective at diluting pollutants because, quite honestly, they're not moving. They get stratified. We get those stratified layers in there, if we remember that. The epilimnion, hypolimnion, and of course the thermocline on the inside. We have very little water flow through there, which means we generally don't have quite as high dissolved oxygen content. It can take hundreds of years to change the water in a lake. And of course what happens is a lot biologically magnified. Eutrophication you should know all about already. Natural enrichment of a shallow lake estuary is a slow-moving system from runoffs like nitrates and phosphates. In a oligotrophic lake, of course, clean. Cultural eutrophication is called cultural because we humans cause it. Nitrates and phosphates from human sources. Farms, feedlots, streets, parking lots can all rush into there. Those algal blooms are much worse when it gets hot weather, or we get droughts for that matter too, which increases the concentration of those toxic substances, the drought in particular, because water evaporates, and then we have increased toxicity. We have increased bacteria at that point. We have increased anaerobic bacteria. Everything just goes to heck. And of course, streams at its worst case. You can see this lovely eutrophied pea green water that poor person is living or get food out of. How do we prevent this? Remove nitrates and phosphates. Great state of Wisconsin. You can no longer put phosphates on your lawn. Legally, farmers can still use it. Unfortunately, they're the main pollutant, or polluters, by the way, but at least we've taken the step where we don't need it. Our soil around here actually has plenty of phosphates. And we can divert lake water to other regions and try to get a little oxygen in there too to keep things moving. Clean up lakes, we can remove excessive weeds, we can use herbicides and algicides, but you hate to add stuff to the water. In some areas you get aerobic bacteria working well. Nitrates discharged from the Mississippi have nearly tripled since 1950, and that's because of people like us putting that on there and getting into the Mississippi Basin. Nitrogen cycle, as I said previously, has been disrupted. We also, in a lot of inland lakes particularly, get blue-green algae blooms, and they're really not too bad for us. But what happens is if you have a dog that likes to eat, or drink rather, out of the lake, it can actually kill them, so be careful of that. We've taken flood control along the Mississippi River very serious, of course. The problem is it's such a huge river system, it flows fast, and we can get increased sediment pollution, particularly heavy metals like to hang around, and of course we can because of this eutrophication. Since 1960s, we've had many areas with cultural eutrophication, again, because our population grows up, we need to grow more food. We like our nice green lawns, too. 1972, Canada and the United States came up with a Great Lakes Pollution Control Program. That's a good thing because, of course, Canada and us share those Great Lakes, and that was a huge fresh water source, with the attempt of decreasing algal blooms, increasing dissolved oxygen, increasing fish catching, catches, I should say, and better sewage treatment plants because of sewage running into there. So with the Great Lakes, what are we doing? Lake Erie, which we'll talk about in a little bit, actually we can start talking about it now, has really cleaned up its act. Lake Erie, of course, which is kind of north of Cleveland and east of Detroit area, extends all the way through Pennsylvania. It was deemed an industrial wasteland at one time because of all the industrial, and that's kind of the steel belt, all the industry releasing all those toxins into it. And it's only like 30 feet deep at its maximum, believe it or not, even though mileage-wise it is huge. And what happened is they did things like pass laws to prevent fewer industrial waste from getting in there. Banned phosphates, particularly household agents that have a lot of phosphates, like cleaning agents. A lot of soaps have phosphates in them. We still have big problems. We still get some raw sewage, non-point runoff. Can't nail people for doing that or get them in trouble. So what's happening is they're getting away with it. We have a lot of atmospheric deposition of pesticides and mercury. Whenever there's coal burning, no matter what we try to do, we're still going to get some mercury in the atmosphere. Pesticides, of course, you spray them right off, or they're going to get up into the air. So the situation I was talking about is right here in Lake Erie, and you can kind of see how this side right here is so eutrophied in there. But we've really cleaned it up, and they've really introduced the walleye population in there and really gotten their numbers up. So now it's kind of like a fishing haven. But even if you look around our region right here, like up in Green Bay, you can see how eutrophied it is there. And look at how eutrophied it is along in there, that green stuff in here. Look at how eutrophied it is and so on. Those areas still need to be cleaned up, so we're not quite done with it. And a lot of that is because those materials very easily. Big problems are the urban sprawl runoff. We've got zebra mussels, which actually aren't the worst things in the world because they do absorb some of these toxins. The problem is they're just taking over so much. And we, of course, have that atmospheric pollutant, something we'll talk about down the road. So what about groundwater? Now, surface water is one thing, but once pollutants are in the ground, it is terrible to get out. It's almost impossible. You have to let it run its natural course. So chemicals used in agriculture, industry, transportation, homes can spill and leak into groundwater. Even around here, think about if it rains out, all those oil little spills from your car that's leaking out, they're going to go someplace and they'll get into the groundwater. You don't want to be drinking that stuff down the road. There's simple ways and complex ways to purify groundwater, but protecting it through pollution prevention is by far the least expensive and most effective strategy. We can try sending more water in, but it's just not very practical. Source of the drinking water for about half of the U.S. population, of course, is in the groundwater, and it can clean itself, but not totally. Once that pollutant's in there, we're going to get it back. This happens even with wells in rural areas of Wisconsin as they get polluted with diesel fuel, for example. And what happens is those wells need to be shut down because people can't drink that organic substance. It's toxic to your body. That, of course, happens in other regions, and we'll talk about some case studies with that too. Some common pollutants are fertilizers and pesticides, things farmers are using. Gasoline, other organic solvents like oil. Fracking is a huge concern right now because we don't know exactly what's being put in the ground to get that natural gas up, and what's happening is that's contaminating wells like out in Colorado and in Pennsylvania and other regions, and I'm sure it is in North Dakota where they're doing a ton of this too. And what happens is they just get dispersed more and more in this widening over more area. Slower chemical reactions in the groundwater. The reason it's slower is, think about around here, groundwater, our recharge area is kind of out in Eagle, Wisconsin area. It only goes, and that's like maybe 30 miles away. Groundwater moves around here at about a foot a day, so it takes forever to get from there to here. So we could have contamination 10 years ago, and it's finally reaching us now, for example. I don't know if that's the exact time, but we don't even know it's there. There's not much dissolved oxygen in the groundwater especially, so aerobic bacteria, which likes to break down pollutants, doesn't happen very well. Not a lot of decomposing bacteria, and of course low temperatures, warm bacterial growth. Just kind of some things that are really wreaking havoc, which I've talked about already. Pesticides, fertilizers from farmers, and quite honestly from us putting it in our residential. Also, buried gas and solvent tanks. So what happens, particularly like along gas stations where they have gas tanks, what'll happen is sometimes those leak. We get leaky septic tanks, which we'll talk about in the second part of this. Maybe a sewage system that's going directly into the groundwater. Somehow landfills sometimes leak. Luckily in the United States now we have sanitary landfills, but that's not the case everywhere. And a lot of times a waste lagoon. So if we have a industry or even like a feedlot, what happens is sometimes that gets out, we have this big lagoon of waste, and of course that's going to get right down into the groundwater. And of course even from mining as it's a serious problem. China, about 90% of the urban aquifers are contaminated or overexploited, so they're taking too much water out, or they're polluted, which is a huge problem. U.S. FDA reports of toxins found in many aquifers. The United States even has our own problems of this too. Nitrate, as I've mentioned before, central Wisconsin, which has sands, which they grow a lot of potatoes on. Potatoes need a lot of nitrates. They put it on there. It's got very high porosity and permeability, so it goes right down into the groundwater, and we get lots of cancer rates increasing in that region. Very slow degrading waste, and of course a lot of it's non-degradable waste, and we'll talk about that when we hit toxicity unit, but it doesn't break down very easily. That's it for part 1.